Hello everyone. A warm welcome. My name is Mark Horton. I'm the PVC for Research and Enterprise here. And it gives me great pleasure to chair this wonderful inaugural lecture, the first of our academic year. I know those who don't necessarily come, and I can see we have family and friends, the importance of an inaugural lecture. I think it's about the most difficult thing that an academic can be asked to give. Partly because it has to demonstrate his great erudition and scholarship and research abilities, but at the same time has to be understandable to a lay audience and comprehensible and take his audience or her audience with them. Now, I'm sure in Kiran's case, we're not going to have any problem, but it is quite a challenge to get. I can remember when I did mine, I was absolutely terrified for years, months in advance. But anyway, a warm welcome, and I think many of you come from a very great distance to be here. Some indeed have even come from the West Indies, I think. So it's great that you can make this very happy and auspicious occasion. And I think some colleagues from the Water Resources Centre are also here down in Swindon. Just to give you a little bit of background about this university, which is rather fun and somewhat quaint. We were actually founded in 1845 at a time of everyone running out of food. Brunel was covering the landscape with iron tracks, and he wanted some food to put on, work out what these trains should actually do. Starving, urban poor. The Irish were all up to it as well. I remember something called the potato blight. So sort of agriculture was really important, and huge amounts of money was pledged by stockholders, shareholders, to build this place. Well, not actually this place, but the Gothic Hogwarts, just a few yards away. This was then put up with a great deal of enthusiasm in the early 19th century, the early years of Queen Victoria. Prince Albert was terribly keen. People came here from all over the British Empire because this was thought to be a model for how agricultural university or agricultural college should be. So a man called Mr. Cornell, Ezra Cornell, came here in 1862 and we thought it was such a good idea that he went back to upstate New York and built a small version of our own called Cornell University. It's got a bit bigger than us since then. But it's model, the architecture is relatively similar. And we have various other outposts which were founded in Australia, New Zealand, Japan, Canada. The list goes on. So we're kind of the mother of the idea of the college organisation, a higher education institute that teaches and researches land, agriculture. And I suppose it was a great pleasure really when Kiran got in touch and said, do you know down in Swindon there's this organisation called the WRC. We actually have a little campus down there, just around the corner actually. Isn't water an important part of land use and agriculture? And by Jove it is, and we can't listen to farmers today without water being mentioned about 3 times a week. So water is so important, and it is great that Kiran has brought water into our portfolio here in the RAU as something which is really critical for understanding agriculture, the future of the environment, ecology, net zero, climate change, and all. So really a very warm welcome to Kiran, but I'm actually going to pass over to Duncan, who's going to give a much shorter version of what I've just done.
Definitely shorter.
Over to you, Duncan.
Yes. Good evening. My name is Professor Duncan Westbury, and I'm the Dean of Land and Property Management here. It gives me great pleasure to welcome you to the RAU this evening for Professor Kiran Tota-Maharaj inaugural lecture, professorial lecture. I think Mark's said quite a lot to actually scare the hell out of poor old Kiran this evening. But we have lots of faith in him this evening. But Kiran wanted me to provide a bit of background to his journey to where he is today and leading to this inaugural lecture. So Kiran grew up in the Twin Islands, the Caribbean country of Trinidad and Tobago, where he pursued his high school qualifications at Hillview College. He then went on to study engineering at the University of West Indies. After completing his degree, Kiran gained valuable experience working at two of the largest Caribbean engineering consultancies, Lee Young and Partners, formerly Hyder Group, and Trintaplan Consultants Limited. Kiran was then awarded a scholarship to pursue a master's degree in environmental engineering at Newcastle University before achieving his doctorate at Edinburgh University. With over 14 years of academic experience, Kiran joined the RAU earlier this year from Aston University. He joined us as a Professor of Water Resources Management and Infrastructure. We are delighted to have Kiran here, as Mark has just been saying, with that affiliation with WRC. And it gives me great pleasure to introduce Kiran to you this evening for this inaugural professorial lectureship.
Thank you. Okay, hopefully this works. Oops. Yeah. Right, thank you, Duncan. Thank you, Mark, for a warm welcome. And welcome everyone from former institutions. Welcome from my family, my wife and colleagues to this occasion. And today's topic is very timely. When I talk about hydrosystems, you'll hear me use it on every single slide of today's presentation. And as Duncan and Mark pointed out, it's a real privilege to join both the Water Research Centre, and I'll come to that in a couple of slides, as well as hold this post at the Royal Agricultural University this year. So just an overview, just to reiterate what Duncan spoke about, my background, my academic background, my journey, the technical topic this evening on hydrosystems and how we can look at optimizations of hydrosystems. And to the latter part of the presentation today, acknowledgements and appreciation to most of you all who are here today. So, to the left is the Cora Water Treatment Works, North Trinidad. My father, a water engineer, we lived about 10 minutes from this water treatment plant. And we had the privilege to swim by the pool just before the intake. Before that water would be taken to the various treatment stages. So there was a pond of where the river would be collected. The water would be sort of a small mini reservoir. And it was quite an enjoyable experience with myself, my siblings, my cousins, jogging in the morning and taking a swim, trying to catch fishes in that section prior to a water treatment works before it. So don't worry, the water was well treated before it went into the distribution system. So I grew up in water engineering, coming from my father's career. It's embedded into me. I would say it's part of my DNA. Educated at primary school level at the El Dorado North Hindu School, and did my GCSE O-levels and A-levels. In those days, we still did the University of Cambridge international exams. So I did usual typical science subjects, mathematics, physics, further mathematics in A-levels, which was the pre-requirements for engineering programs, all engineering programs at the University of the West Indies. So my academic background, bachelor's at the University of the West Indies, and I'm quite proud to say today, University of the West Indies still holds British accreditation since 1930. And the former president of the Institution of Chemical Engineers once said, you want to do chemical engineering, you go to UWE St. Augustine. I had the opportunity to do my MSc at Newcastle University, and a very good experience there, and my PhD at Edinburgh University in the Civil and Environmental Engineering department. My first lecturer job started at the University of Salford, where I did my PG Cert. And my parents' photo to my left, to your right, visiting me at my first job, quite a proud moment for me, giving them a tour of University of Salford and comparing it to the University of the West Indies, what they had and what they were missing. And And part of it was also starting the MSc PG Cert, PG Dip in Water, Energy and Waste, a program which we attained with my team and colleagues, JBM, the Joint Board of Moderators Accreditation. And because of departures and staff moving on, including myself, the program had to be sadly shut down. I moved on to the Abertay University, Dundee, and my boss slash mentor colleague is here with me today, traveling 7 hours from this group. Wonderful research experience in anaerobic treatment of water, wastewater systems, being involved at both bachelor's level, MSc, and PhD level for students looking at wide ranges of relevant topics in wastewater systems, water reuse, quite a novel topic in those days. And the picture to my left, to your right, is my wife and I touring around in Dundee. Moving on, had too much of a fun time at Dundee, then the fun continued at University of Greenwich. My colleagues are here today, and I think made a lot of positive outputs in Greenwich. Wonderful colleagues, and I'm proud of that. They've joined me today for this event. Working well with my students, postgraduate students, PhD students. You can see some of my visiting students from France there working on solar water disinfection methods. Charlton Athletic, which is an RSK group, we got free football t-shirts and free tickets going to the game. So that's my Greenwich t-shirt. So I'm proud of that as well. And thereafter, I was appointed head of civil and environmental engineering. So more admin related, lost research opportunities, but good support from colleagues who are here today as well. So the photo to the right being there at the start of COVID, where we shifted like every other institution, working towards delivering or trying to help our students go through difficult times in COVID. But I think it was a good learning curve for myself at West of England, line managing staff, technicians, and going through a wide range of admin within this post. Thereafter, I was hired at Aston University as Associate Dean for some time and Reader in Water and Environmental Engineering, and I'm quite pleased that my former boss is here, from the former Dean, Professor Sarah Hainsworth at Aston before she ran away to University of Bath, and making us all sad at Aston. But at Aston, the research continued. We had good development of programs, B-Eng, M-Eng programs in civil engineering, MSc programs in sustainable engineering. And of course, part of the job is education and working with students. And this is the fun part of the job always. So just a brief overview of my research areas. So I've been working on statistical models, hydraulic models for water, wastewater distribution systems. Various PhD students worked on this project, including support from the Environment Agency. The impact of water demand, the impact of your network, the asset itself. There's so many research questions still being asked today. Leak detections, non-revenue water, pipe materials and contamination. And the list goes on and on and on with water and wastewater networks. Also worked with students working on what you call quadratic sludge-based reactors, mainly used in wastewater treatment works, and how these behave under various hydraulic loading, as well as in the Caribbean region, for example, Haiti, where the structure itself, the critical structure itself, has to withstand seismic forces, earthquakes, alongside hurricanes and other natural disasters. Both at Abertay University, Salford, came up with this concept, how we can implement constructed wetlands or engineered wetlands with water source heat pumps. So this gained good momentum. We had few postdocs and PhD students working in our teams, measuring both the stormwater quality, the thermal performance and the behavior. As for those who may know, ground source heat pump, it's something that governments have been pushing to replace gas boilers as well, and how these can be implemented into systems such as constructed wetlands or biofilters as well. So moving on to the technical topic today, hydrosystems, how we define hydrosystems. It's everything. It's both your natural water systems, your surface water, your engineered systems, dams, locks, lakes, groundwater reservoirs. It's the lifeline of our planet. As I often tell students, we live on a water planet. Water comes first, yeah? We're not on Mars. What are they looking on the planet of Mars? They're trying to find water, H2O. It is a critical resource. It binds us together. It brings and breathes life in our country's society as a whole. And when we talk about integrated water management or integrated water resources management, it intertwines everything that was water related. So interconnected hydrosystems, how do we optimize this? Today, more than ever, countries across the world, we are not paying attention to our water systems, our hydro systems. Both surface water systems, looking at changes, the urbanization, the industrialization, out of sight, out of mind, especially groundwater, which I'll come to in a couple of slides. The water is changing, whether you want to believe it or not. Evapotranspiration rates are changing. Infiltration rates are changing as well too. So the climate is becoming more and more difficult in terms of how we manage our critical resource. We cannot go for more than 2 to 3 days without water. Yeah? This precious resource here, it's critical. It's more important than mobile phones. You can see in some of the developing countries across the world, they have now access to 5G and 6G, yet still they are still struggling to provide surface water supply for their countries. So global water conflicts is a real thing. Wars are being fought over this still today in Africa, where you have river basins and catchments crossing. Countries are against each other for certain things, and water is one of those pressing issues across the world. So all hydrosystems are interconnected. How do we look at optimizing this? How do we pay attention to bringing it back to its natural state? The temperatures are impacting it. Less rainfall, more rainfall, flooding, drought. It is difficult. And for those who are from Trinidad and Tobago, I'll say one thing here. These sharks are saying good news because the water is rising, yeah? But for those who are from Trinidad and Tobago, we eat the sharks, yeah? So it's good news for us, bad news. Okay? So interconnected hydrosystems and optimization. A hydrosystem defined as any structure or volume where water is. It creates that boundary. It intertwines with other sectors as well. For example, water, energy, food. When we look at water resources management, 90% at the top of the slide of all natural disasters are water related. By 2024, one in 4 kids would be living in an extreme high water stress zone or high water stress country. So water resources management, the understanding, the applications of science and engineering principles, it's known, but it's sometimes being ignored. How you can improve water resources planning, how do you deal with hydrosystems, and you look at this slide categorized in 2 areas, water control, drainage. Certain parts of the UK are still experiencing flooding. For the first time in 50 years, Oxford train station has been flooded, right? It has never experienced that level of rainfall before. How do you use water resources both for domestic supply? Drainage, irrigation. Hydropower is becoming less and less of a challenge today because countries are moving a little bit away from hydropower. Recreation, fish, wildlife improvement, and the watershed management. When we talk about circulation, water can be reused. The infrastructure is there. The technologies are there. To capture water, for example, in Singapore, they have been reusing their wastewater. 100% of their wastewater is being reused. Treated to full, all pollutants being removed back into your potable water network. So a comparison reported from the BBC a couple years ago, you can see on the pie charts the States versus the UK, 70% of water supply versus 22% for domestic. In the States, 70%, like most countries, 70% is that use where your water supply, fresh water, is fed directly to agriculture. In some countries in the Middle East, there's even desalinating water for agriculture. And in the UK, it's slightly less because of the change of the industries itself, but it's still a large consumption of water resources, fresh water resources going into food and the agricultural sector. And you can see the bar charts they left from 1990 to 2000. Agriculture has been dominant worldwide. So the average country and the average water use goes to 70% targets for agricultural purposes. How do you deal with the two extremes? Yeah, there are two extremes, and the UK is experiencing these two extremes as well, especially during the summers. Parts of the southeast, there are pressures, there are hosepipe bans that occurred during July and August in Kent and certain parts of London as well. Longer droughts, drying up springs itself, and then excessive rainfall. And this is because your evapotranspiration rates have changed. Your precipitation patterns have changed because you have urbanized your areas. You have changed the natural geology, the natural hydrology in your systems, in your natural ecosystems. This chart, 1950 to 2017, millimeters of rainfall per year. Yeah, and you can see as the years go by, that those countries, the shades of orange, the shades of yellow, is slowly becoming orange, which is elevated levels of drought, less rainfall, and slowly to red. And what is happening across the world, where it's already red or orange into red, less and less rainfall, the automatic switch on like this. A country thinks, you know what, we're not getting enough rainfall, we need to get a desalination plant, yeah? That's just the normal go-to. And it is not the solution. For example, countries where we're from, Trinidad and neighboring Grenada, there's enough precipitation, enough rainfall. If managed properly, if interconnected wisely, you can have enough abstraction into your water supply network. There's a direct correlation between surface water and groundwater. There's a direct relationship between precipitation, both snowfall, rainfall, yeah, and the amount of water that can be provided for both domestic use, agricultural use, and industrial use. But far too often, a lot of utilities, as well as civil engineering firms, contracting firms, they do not think about the ground, yeah? From even land use as well. When you talk about the ground, even in the agricultural practices, when you compact soil, the infiltration rate changes, yeah? When you remove the natural vegetation, the infiltration rate changes, and your groundwater changes. And what happens in this catchment will affect something 1 kilometer down the road, 2 kilometers, and so on, causing cavitation, causing sinkholes, causing major disruption. Just last year alone, in Bengaluru, India, what shut down their Silicon Valley was water. They constructed on their water tables, they changed the water tables and the water depths. They've made mistakes. So infiltration from your soil, feeding back underneath the ground, finding its way back to the surface level, have shut down India's IT district in Bengaluru. Similar cases have been seen in China, yeah? Excessive abstraction of groundwater causing sinkholes and major disasters from your ground. So percolation rates, and I put this slide because I think it's important for people when we talk about water, we must understand the ground is important. And I was talking to a colleague earlier today. I always smile when I see someone, I have a wonderful conversation when someone comes from a background in geology, geotechnics, soils, yeah? It's not my area of expertise, but I love that they're in it because they're so important to all subjects. They're interconnected to water as well. So when we talk about geology, when we talk about geotechnics, when we talk about soils, it is a critical part of water. And we need them in our teams, in our research groups, in our research clusters, as well as industry to help understand hydrogeology, right? Groundwater pollution and groundwater abstraction. The water balance is simple. It's not that difficult. Infiltration I minus outflow is change of storage with time, ds/dt. And as we as human beings, we change this. This is not being changed by nature, it's being changed by us. We are altering our simple water balance equation. And how do we fix this water balance equation? Now we start thinking, yes, desalination, applicable to certain countries, rainwater harvesting, looking at how you change your evapotranspiration rates and reducing it or normalizing it, efficiencies in irrigation and vegetable applications to the vegetation and when you're growing vegetables and other agricultural crops and so on as well. Price control, increasing the price of water, which is what Thames Water is thinking about as well, right? Drought forecasting, all of these things are methodologies that can be looked at in augmenting water supply. When we talk about hydrosystems vulnerability, the vulnerabilities and risk is a lot. there's too many to count, from flooding, groundwater pollution, wastewater, yeah, droughts, etc., impact to your hydraulic structures, and the list goes on hydrosystems vulnerabilities. Where do we start? Where do we stop? Climate change, as you can see on the GIF below, and the amount of flow happening both in the largest rivers, the amount of pollution coming into these rivers, the amount of changes and question marks about unknowns. It is a lot of things that is being altered, impacting our hydrosystems today and over the last 20 plus years. Yes, our population is growing. With population growth comes water demand and water use, as well as wastewater as well. How do we look at this in terms of sustainable use of water, but also sustainable management of wastewater? When we talk water, we also need to talk wastewater. They go hand in hand, they're siblings. So as you consume water, you generate wastewater. As I stated before, the evapotranspiration rate is altered because of your changes in cloud cover, because of your alterations in precipitation levels as well too. So you can see on the graph to my right to your left, in some cases you have that actual evaporation rate, expected evaporation rate, and monitored or changes in your precipitation levels. You have meters like lysimeters and other technological kits that you're expected to use on site. And it's important to have measurement devices when you're on site, because as I told colleagues in the past, everything can't be assumed to be modeled. Measurement is key, and accuracy in data control is important as well too. How do we measure? How do we predict versus measurable of water gains, flows in and out of a hydrosystem? How do we pick up on these things? And it's critical to have the right sensors, data collection, data analytics with water, with precipitation, with changes of your flows. And you can see on my right, your right, sorry, 100 years storm event. And you can see houses built where encroachments comes in, the natural flow of the channel. As that storm event hits, 1 in 70 storm just happened a couple of months ago. The London Tube is designed to have a 1 in 200 storm event. Yeah? So it means that if your rainfall exceeds that amount, the London Tubes will be flooded out. But how do you continuously design for 1 in 100 year? Yeah? Are you paying attention to the natural flow or the natural precipitation itself? When you change grassed areas and you place concrete, this is well understood. You change the temperature of the entire catchment. The entire urban environment, you've altered the precipitation level. You've changed the actual average temperature of that area, of that zone. This equation, the Horton equation, again used for infiltration. And the Horton equation is a function of your equilibrium or average infiltration rates versus your constants representing decreased infiltration capacities. T is time, so you have that function of expected infiltration over time and an exponential decay curve there. The infiltration capacity by Horton's equation is still used in software packages today. Yeah? So the challenge with this is that when engineers go and they run this and they use and they pick up on Infosys or some such software, they run it, it's using this equation, it's giving them an expected infiltration on this type of soil, but they're not paying attention to the soil type, the changes, the historical changes. What is underneath that ground further? Yeah? Has there been underground pipes running? Natural gas pipes as well. The overall infrastructure has changed over the last 20 years in that particular catchment. So how effective and efficient would be the Horton equation? And this is where mistakes occur, that you're using equations and it's embedded into software packages and it's not giving you valuable or reliable data. When you look at hydrosystems as well too, from culverts in drainage systems, hydraulic bridges, dams, etc., you are seeing the return period, which is the time these hydraulic systems are designed for. They're not meant to be everlasting, forever and ever. The timeline for these hydraulic systems are ranging from 5-10 years to maximum 100 years. And how do we look at this to monitor it, maintain it, is a key word that came up in our last conference. Maintenance, critical to our water and wastewater infrastructure. So when I use the word critical infrastructure, I've spoken about this before, about water and wastewater. Water systems, this shows you a conventional water treatment works. Intake, abstraction, goes through stage 1 treatment, stage 2 treatment, disinfection, and into your distribution system. Another example of critical infrastructure, engineered hydro systems, example from Oulu in Finland, using a combination of granular activated carbon, a series of treatment, etc. Now, I put on the bottom of the slide, forever chemicals, yeah? This is conventional treatment plants, yeah? When we talk about forever chemicals, the perfluoroalkyls that are found, yeah, these are from pharmaceuticals, the list goes on. One of the most difficult things in water and wastewater treatment is dealing with the chemical pollutants, yeah? It is not that easily removed. It is embedded in a soluble state. I often tell students as well to physical, biological, it's known. You can remove it, you can treat it. But when it comes to unknown chemicals or the cocktail of chemical pollutants that is exiting every single country, including the United Kingdom, this is a real statistic. This is not my statistic. 80% of the wastewater coming across the world is leaving untreated right now. And this has been happening for the last 15 years. Are we aware of the impact of your hydro systems, now your oceans, yeah? The downstream seas and oceans, yeah? When you start and looking and thinking about this, the level of pollution, the impact, it's quite difficult to comprehend, and it's quite challenging. I put up this slide as well. Every time you buy a new suit, I'm proud, this is my first suit in 5 years, yeah? Right? You pay attention to your footprint. Every time you buy a new t-shirt, there's a footprint, there's a wastewater that feeds into this industry as well. So 20% of the wastewater in the world comes from the fashion industry. Water and environmental engineers, in terms of their response, is how do you deal with this? Very often, colleagues in WRC and so on as well will come up with a matrix, have solutions, yeah? What type of solutions you would think about dealing with this waste product? Can it remove the desired pollutants that you want to remove it? The cost is the biggest factor in choosing these systems as well too. So the water and environmental engineers' response in dealing with water supply and wastewater has always been sort of not so conventional in some cases, but also conventional in a lot of other countries. Whether you have centralized wastewater and water treatment systems, partially centralized or fully decentralized systems. The water and wastewater infrastructure is interlinked. So you can see in some cases when we talk about combined sewers, or combined sewer meaning taking the drainage and the stormwater, mixing it with your wastewater and sending it into a treatment works, that is what should be happening. Yeah? Far too often when it rains and it's excessive water, you are bypassing it. Yeah? So you see on the slide, yeah, wastewater coming into treatment stage 1, 2, 3, 4. And just imagine that 80%, it's actually bypassing 4 stages of treatment, entering your rivers and your oceans. And it's quite toxic because we don't know all of the cocktails of contaminants that are entering our natural hydro systems today. The need for nature-based solutions is understood. People have been applying constructed wetlands in wastewater for a long time. Plants themselves, we are at an agricultural university, the power of plants is slowly coming back to UK water and wastewater utilities. Yeah? Utilizing plants and constructed wetlands, reed beds within the grey infrastructure, how they can help absorb and remove contaminants and pollutants. And it's quite important as well. As I mentioned before, how accurate our models are based on changing evapotranspiration rates, changing temperatures, picking up data and accurately picking up data so that we can monitor and maintain our systems more effectively and efficiently. So on this chart, you can see the discharge, your flow, in terms of liters per second or liters per minute or meter cube per second or meter cube per hour. Agricultural areas, I would say not so bad. Urbanized areas, quite fast. Yeah? as you put down a house, and I remember living in Bristol when I was at University of the West of England. There was a contractor, new development, and this was a couple of years ago, and there was no sustainable drainage systems, yeah? Roof, fast runoff, into tarmac surfaces, concrete surfaces, and then into your drainage, yeah? You're actually speeding up the water, leaving your catchment. You're encouraging flooding, yeah? So it is understood in terms of sort of slowing down and managing flooding, but it's quite surprising that today lots of contractors bypass it and they don't apply it. When we talk about the environmental impact of our hydro systems, it is important. At our recent Sustainable Drainage Systems Conference, a PhD student from Edinburgh is monitoring in Scotland the Inuit and 3 different types of frogs, their native species. The road runoff feeds into their wet ponds, yeah? The more and more pollutants gets into that, impacts on your invertebrates, your other organisms, your aquatic organisms, etc. How do you monitor and measure your pH, total dissolved solids, and your dissolved oxygen? For those who may not be quite savvy in water, once the dissolved oxygen content is less than 5 milligrams per liter, it's unhealthy. No fishes or aquatic organisms or frogs, etc. can survive. Yeah? So the health and well-being of the water is critical to the state of those hydro systems embedded on road runoff, etc. When we apply water management models, there are critical questions that we must ask. Yeah? What is the use and the best use of our water infrastructure? How are we going to manage that water resource? The operational constraints, rules and regulations in that country or in that catchment, and how we can sustainably manage both water for agriculture, irrigation, as well as energy. So a hydraulic model or hydro systems model needs data to be fed in it. You can't just magically think about numbers. This is our rainfall. This is our historical rainfall. And reliable data is a challenge in the developing world. Yeah? Historical charts, historical rainfall data is difficult sometimes because it's not properly monitored, maintained. There's very poor archives of your water systems. But it's the key in terms of predictability of any hydro system. So you can see on this slide, rain gauges, atmospheric sampling from your humidity levels, your temperatures, etc. And feeding into your systems is needed. Various types of sensors that exist both in urban and suburban areas for hydro systems monitoring. So when you're looking at applying a model, the accuracy is dependent on where did you get that data from. Very often I told students, you know, I've done my bachelor's degree, I've done my MSc, I've done my PhD, I have 20 data points or 30 data points. That is not enough. That is not enough to even give you a statistical analysis for this particular catchment. So water, you need to do hundreds of data points, yeah? Historical, over 5-10-year periods to pick up on that behavior, on the real input versus the simulated input of that water system. And you can see on the graph, that is a 5% error in predictability. 5% makes the difference between surface water flooding in a 1 in 70-year storm event versus proper infiltration. So moving on, some projects coming up in the UK based on dealing with hydro systems. This is the state of a reservoir in Londonville in 2020. And as part of this challenge, the UK has decided that they're going to build 3 big, massive reservoirs within the next 30 years. And I hope the current government sticks to their words and you know, don't fool us like they do in Brexit. That water is critical and we need to get these reservoirs constructed and built for the long-term sustainability of supply. Southwest Water has plans for a desalination plant. That was on the BBC just a couple months ago. And moving closer to my home, this is earlier this year in Grenada, our smaller Caribbean island, not very far, half-an-hour flight from Trinidad. And again, you can see their reservoirs. Change in precipitation for those who follow cricket. This is the rainy season. We're expecting to get rain. Yeah? They've never experienced this drop in their reservoir before. So much that they're out of mind, out of control. What do they do? There's no desalination plant in Grenada. This is their main reservoir. Where do they go? Here in Trinidad, The reservoir depths, again in the rainy season, I keep on following it, and they're saying 20% down. Yes, the rainfall is changing because we are also constructing, right, and building and changing our natural environment and our natural hydro systems. So employing a good or best practice hydro systems management model, it's interconnected. It's everything around us. It's understanding rainfall. It's also, when you do drainage, when you think about wastewater as well, it's creating circularity in your systems, right? It's understanding the impact to your natural environment, the impact to aquatic organisms as well. We can improve our hydro systems. We can optimize it. The solutions are there. I'm presenting in front of lots of my former bosses and colleagues who are very experienced water engineers there, and I'm seeing them nodding. So I think I'm right, yeah? They're saying that the solutions are there to optimize hydro systems, from catchment models, from looking at the ecological and the environmental engineering aspects of your hydro systems, and to improve it. When we talk about water, just a few points. Water sits in the middle of both your energy sector and your food sector. It's just there in the middle. As I said before in a previous lecture, I like to use water, energy, food. WEF sounds nicer, yeah? But in reality, it's actually water, food, energy. But it sits right there in the middle between these industries. And how do we implement a water, energy, food nexus to balance these industries, these sectors, these critical resources more sustainably? Different countries look at it. Your footprint, everything has a water footprint. Everything has a water consumption and abstraction to it. More so, as I stated earlier, 70% feeding into that light salmon pink circle, which is food. Water feeding directly into your food sector as well as the energy sector. It is a learning process, our WEF. There's much more to be done between these industries. We have to look at it holistically. We have to look at it differently. What was done in the past, especially by civil engineers, needs to be changed. That's why the word environmental engineering exists. So implementing a water, food, energy nexus, and recently they've added, just 2 years ago, they've added ecosystems, yeah? So now it's called WEFI. So water, food, energy, ecosystems, we have to remove ourselves away from traditional high carbon footprint civil engineering activities, high carbon footprint oil and gas activities, etc., thinking about our water systems, thinking about the water and wastewater that we as human beings generate and the problems that we create for ourselves and the future generations to come. It is solvable. There are solutions, and this is where our role as universities and research centers and groups have to be looking at the behavior and the use of water in all of these sectors, how we can implement carbon neutral systems in both the energy side as well as land use, the need for more reforestation, biodiversity, and agriculture feeding back between water and food. The value of water, of circularity, how do we measure this impact? The digital footprint of water can be easily monitored now in terms of the average consumption patterns, yeah? And other key technologies and smart technologies such as apps, sensors, and AI, yeah, feeds into our behavior and reinforcement of sustainable water resources. We can optimize this as scientists, as engineers, as universities, as practitioners, looking at how do we deal with now, today, droughts, water resources management, flooding, capturing that water, storing that water, and changing the way we use water with green-blue infrastructure, nature-based solutions, as well as preparing ourselves for the current natural and future natural disasters that several countries face today. So the latter part of today's inaugural, I need to talk about the Royal Agricultural University. Yeah? I'm very proud to be here today, a very historical university that Professor Mark Horton mentioned and Duncan spoke about as well, driving the next generation to deal with uncertainties in our natural environment. And I want to just bring you all, this is the academic and the engineer in me, yeah? This book was published in 1992, And some of the modules in the 1840s, 1850s, 1860s, these are the list of the modules that students enrolled in. Practical agricultural infrastructure, geometry applied to surveying, mechanics, hydraulics, drainage and infrastructure, geology, mineralogy, natural history, principles of veterinary art, which is veterinary medicine, and methods of farm account. And I took from their past papers and I solved this. Yeah, this is me having some fun. And I just wanted to show you the past papers from 1870. To the left, I have the question that the professor asked in agricultural chemistry. The question says, what are the chief defects of precipitation processes in the treatment of sewage, which is wastewater? So these are my answers. I think I'm right, yeah? Sludge generation, chemical use, pH temperature sensitivity within your water, nutrient removal. So when we talk about nutrients, nitrogen, phosphates, etc. And the last part of my slide, I said, in those days, they weren't talking about forever chemicals. So we have to add this on now to our response of this question. To the right, mechanics. Yeah, that question asked in that 1870s past paper, how long will it take for an engine working at a rate of 8 horsepower to raise 10,000 gallons of water to a depth of 165 feet? I don't think in those days they had scientific calculators or formula sheets, but there you go, yeah? They had to convert definitely from the American units of feet to meters, yeah? They would have had to change the work, calculate the force by distance, and hopefully get a good answer 5 minutes and 9 seconds, yeah, to get the solution of what they had to do in those days in the 1870s. So quite a good history that right here in Cirencester, these students face these exams, yeah? I don't know how this generation will face if we put back these questions to them today. So a good history. A lot of programs, postgraduate programs, undergraduate programs here at the RU, we embed the water, energy, food, and ecosystems nexus into the educational structure. I think RU colleagues, academics, professional folks, and so on as well, are quite proud about having these types of programs within their undergraduate, postgraduate delivery. And recently, alongside with support of my colleagues and the help of both the Water Research Center as well as colleagues here at the Royal Agricultural University, we are quite pleased to launch the UK's first MBA in water management. We've actually, with my colleague, Dr. Beverly Hill, here, who's here today, we've already gotten the program accredited, and we're aiming for other professional bodies to accredit this program. So quite pleased, we do have some students on the list. We need to get some more students, and my colleagues from both WRC and RU are helping me to get that in terms of enrollment. So we are very proud of what we've created, this new MBA in water management within a joint program between WRC and the RAU. A little bit of history with the Water Research Center. 1927, so in 2027, they'll be 100 years old. A lot of innovation, research, for those who don't know who the WRC are, my colleagues are sitting here today. Very historical institution. It used to be government run until 1989 when Margaret Thatcher privatized all of them. And their role was to oversee the activities, the work being undertaken by your water utilities, wastewater works, etc. So a lot of innovation applied with WRC. I was quite fortunate as an MSc student at Newcastle University to do my MSc with WRC, traveling down to Swindon and working on real projects, on drainage projects and stormwater management projects in 2004 to 2005. So a lot of activities in the operational space of WRC, and it's a wonderful opportunity for me to sit with so many colleagues who, like me, can talk about water for like 10 days straight, yeah, without thinking about anything else. So quite a wide range of activities from the WRC. Wastewater, water quality, modeling, the technologies, desalination. My colleague is here from desalination as well too. And the knowledge network with the head of academy who's here is growing. So you can see this slide, I've actually added on Royal Agricultural University. Like myself, WRC is still supporting postgraduate programs at Newcastle University, at Cranfield. So it's great to see my colleagues at the WRC working with academic institutions here in the UK and internationally. So, almost to the end, but I need to say a special thanks to a few colleagues here who surprised me, by the way. So I want to start off with a couple colleagues from Aston University, my former Dean, Professor Sarah Hainzo. Thank you very much for coming. And in front of all my colleagues, I will say this openly and publicly that I became very sad when you left me stranded and isolated at Aston, but I survived. and Patricia is here too. Thank you very much, Patricia, head of the Ebry Center at Aston University, one of my very supportive colleagues here. And my other colleague sitting at the back, Professor Satya Shah from Royal Holloway, he surprised me. I didn't know he was coming today, so thank you very much, Professor Shah and his wife for attending today. You've been a wonderful colleague to me over the years and former colleagues at Greenwich. But we've reached a bit of family. I want to pay a special thank you to my wife. As you can see, it's been a 14-year journey, but during that 14 years, we were like hopping right across the islands of the Great British Islands, yeah? And this could not have been done without my wife, Sapna, standing by myself, helping me, supporting me, going through lots of interviews and challenges, but, you know, both success and rejection. And I want to mention this as well, too. 9 times interviewed for prof level, yeah? 9 times coming second. And I think out of the 9 times when I was interviewed for the university in Iceland, I think deep down she was relieved, yeah? so I wanted to just mention that today. She was quite happy I wasn't going to take her to Iceland for a job. And a huge thank you to my family, my mom who is here, my dad who is busy seeing about the Salcott stuff in Trinidad, who couldn't make it, and he said to me, he's seen me present enough today this year in the Caribbean, so he knows a lot about what I do. But also thank you to my sisters, both sisters and their families who are overseas at the moment in the States. And some of my wife's families who are here, her uncle and aunt from London, as well as my cousins and my mom's sisters. I'm really appreciative of you all flying from the West Indies as well as the United States for this event today. A huge thank you to our gurus, our spiritual gurus, my godfather as well too, Pandit Kiran Tota-Maharaj from Trinidad. And we have a very good relationship with Pandit Sharma from the Manchester Hindu Temple, as well as my cousin as well too, who's a Hindu priest, a Hindu Pandit as well, who's supported us over the years, especially during our difficult times. I want to say a huge thank you to Professor Colin Hills. I like to put his middle name in. I don't know if he picked that out quite often in our journal publications as well. I would put Colin Douglas Hills, but I have to thank him for his support over the years, you know. It's been wonderful working with him today and always. We've had a wonderful career of research, of applied research, both at, going through rejections with the research councils as well to success, working with Colin over the years. And I'm really appreciative of you and as well as Dr. Namisha for joining myself today for this event. So thank you very much, Colin, and I hope to continue to work with you for the next few years as well. And Professor Kit Pipon is my undergraduate lecturer who is trying to convince me to come back to UWI, in Trinidad. But he has been quite supportive to me over the years from support from undergrad, MSc, PhD levels. And I have to say thank you very much to Professor Kit Pipon. My thanks have to be extended to Professor Chad Stadden, who is here from Bristol. That's Chad and myself. Every time our PhD students would be successful, we would have a pint. I think I paid for the pints most of the times, yeah? And to the right, my good friend, former line manager and colleague who traveled 7.5 hours today from Dundee. He's here with me today, and, I have to apologize to all my colleagues for leaving them alone, but I told you, by me leaving, I've made more friends, yeah, at the same time, and I've kept my existing friends as well. So I want to say thank you very much to Joe and Chad, wonderful colleagues, wonderful engineers and academic practitioners, and it's been great fun, and we continue to have fun in research. And now to my WRC colleagues, yeah. Andy isn't here because I had a little comment, yeah. This is Andy before I started, this is Andy when I started 1 year later, yeah. Okay, right? So my colleagues, of course, at WRC, Ms. Nicola Richards is here from the head of the academy. Sean sends his apologies. He's in South Africa, and Simon as well, too. A huge thank you to you all for your support on developing this partnership between RAU and WRC. And here we have Professor Mark huge thank you as well too for supporting this partnership and this position. And we have a wonderful VC, Professor Peter McCaffrey, very, very nice guy. And Dr. Esther Wilkinson and Professor David Main, who are also part of this journey and the development of programs here at the Royal Agricultural University. So I just want to dedicate this presentation to my late brother who passed away in 1999. Maybe I would not have been doing engineering if this didn't happen, but I'm dedicating this to him. And it's been a wonderful journey. Thank you very much.
Thank you very much, Kiran. That was a tour de force. And you achieved both achievements. You made understandable, but technically scientific.
Thank you.
So an amazing lecture, and really so fantastic to hear about all your history and the immense potential and challenge that the water has to us all as we move forward to a new world. Now, I don't think it's the custom in inaugural lectures to have questions, because I think we have a small reception in the Bootflower Hall, do we not?
Yes.
And I think the best thing would be that we all quietly move towards the boot, where I think Van d'Honneur will be awaiting us there. So thank you once again,
Thank you.
Kiran.